having understood what central limit theorem means, now we can embark on what we call statistical inference. All right. We can embark on statistical inference. This word means what? It's basically what we call a guess in the common language. But obviously in statistics, we are not going to make guess, but when we talk about guess, it's mostly a formal kind of guess if you want, but it's going to be an estimation that you're going to carry out. An estimation of something that is unknown. An estimation of something that is unknown. This is what we are going to do. We are going to make an inference on something that is unknown. And for that, we are going to go through two possible ways. In fact, there are three different ways. But for the first way is the point estimation. This is one way. You also have interval estimation, and you have something else that we call hypothesis testing. All right. So all these are different ways of carrying out statistical inference. And today, of course, we'll start by point estimation. Now, when I refer to the term unknown in statistics, we generally refer to these as parameters. An unknown quantity is what we refer to as parameters, all right? So we are going to kind of estimate these unknown parameters. And in statistics, what we have different parameters that exist. We have a parameter for the mean that is described with the Greek symbol mu. There is a parameter that is used to describe the population variance. Now, this is the population mean. This is the population variance. And so population mean, and this is the population variance. We have a parameter that is used to describe the standard deviation, which is sigma. All right, this is sigma, a Greek letter that we call sigma, small letter sigma, and then sigma squared in this case, and this one is sigma, which is our population standard deviation. And then there is another parameter that is used to estimate the population proportion. The population proportion, which is P, but it depends on different books. Some books use the term pi. There are different notations that are used, but in this lecture, in this course, we are going to use the notation P to describe the population proportion. So we might want to estimate a certain population mean. We might want to estimate a certain population variance. We might want to estimate a certain population standard deviation, or we might want to estimate a population proportion. We also refer to these as the true mean, or the true variance, or the true standard deviation, or the true proportion. All right. So we do have the true value, but very often, because of different reasons, we don't go and make a census to get all the data. So we want to take a sample from the data, and when we take a sample from the data, this is where we come to the concept of estimation or inference, because we don't have the exact value. We don't have the exact value for these mean, variance, standard deviation, proportion. So what do we want then? We want to estimate them through a sample. That is basically what we want to do here. Here we want to estimate these different unknown quantities that are referred to as parameters through some measure that we will refer to as statistics. All right, as statistics. And also we will refer to them as point estimators that I'm going to get into in a moment. All right. So just bear in mind what we are trying to do here. We want to do an estimation, and this estimation can be done through either a point estimation or through an interval estimation. We will start by the point estimation to discuss a little bit what it is. Now, what is a point estimator? Normally, a point estimator of a certain population parameter is a rule or formula that tells us how to use the sample data to calculate a single number. Look at this, it's very important to note that. A single number that can be used to estimate the population parameter. All right, we'll get back to that in a moment. But let's try to understand what is said here. A point estimator is is a rule of formula that we'll use. For example, let's suppose I want to estimate the true mean mu, which is our parameter. All right, and if I want to estimate that true mean mu, I may decide to use a certain formula that will enable me to estimate by a single number what you have for mu. And one of these possible formula is by taking sum of x over n. By taking the sum of x over n from the sample, you are able to estimate what you have in your population. So the sum of x over n is our x bar that we know. This is our statistic, which is the point estimator itself. That sta This is our statistic, which is our point estimator itself. Note that this is not the discipline that I'm talking about. It is a measure. I did not put a S here because it's a measure statistic, all right, that is used to estimate a parameter. And this estimator, we generally are going to define it with a small cap, all right? When you put a cap on something, it means that you are estimating something. So mu cap is an estimator of mu, and mu cap is equal to x bar, which is equal to the sum of x over n. Remember that our point estimator, which is mu cap, should be a rule or a formula that enable us to estimate with a single number what you have in your population. So this is what we got. We've got a rule or a formula, but it's very important that you note something, that this rule or this formula that we have to use should not contain any parameter here. In other words, you cannot estimate a parameter with another unknown here. You should always be estimating this parameter through something that is observed in your sample. All right. You cannot have, for example, any formula like, for example, something like that, mu, sigma. All right. You cannot have a formula like this. That doesn't make sense because you can't have a parameter again in the formula, or you can't have sigma something, for example, here, because sigma is a parameter, it is an unknown, so you can't solve this by something else that is already unknown. This is very important to know because these point estimators that you are using are what we call statistics, and statistics are not does not contain any parameters or any kind of unknown in it. Now, for the point estimator, as I said, you will represent it by a cap on it. And this is what I explained here, but this is a general definition. All right. It's a general definition, which is for any point estimator. It could be sigma squared cap. It could be sigma cap. It could be p cap. All right. It could be anything. So this is why we used a different Greek letter theta here to describe any possible estimator. Now, you have a point estimator, and the value that you get from the point estimator when you're going to compute this value, the value that you're going to get from the point estimator will be what we call the point estimate. All right. The point estimator is the rule or the formula, and the value that you get from it represent what we call the point estimate. Now, it's very important that you understand certain principles about the point estimator. As I said to you, this is an example of a point estimator, all right? This is a rule or a formula. But nothing prevents me, let me just give you an example, nothing prevents me from using another rule or a formula, suppose n minus 1 or n minus 2 or something else that could be used to estimate mu. But we have to be careful. If we use any formula, they might not have a properties that is desirable to estimate that mu. So we need to have our point estimator to have a certain properties that are desirable to estimate that mu. For example, sum of x over n is relatively intuitive to understand that it is appropriate to estimate mu. But still, we need to know whether this is really appropriate. And one way of knowing whether a point estimator is appropriate is that it should abide by three different principles. One of it is what we call unbiasedness. Another one is what we call efficiency. And another one is what we call consistency. These are three different principles that we want to try to abide by in view of doing a certain estimation. And we'll try to discuss these different concepts here. All right. So let's start by, first of all, unbiasedness, the concept of unbiasedness. As I said to you, we want to ensure that whatever estimator or rule or formula that we are using, we want them to have these different properties. It may happen that sometimes some of them might not have all of these different properties. And then it's okay. We can still work without some of these properties being satisfied. But still, we want to have them as far as possible. And let's suppose I was talking about the mean. To estimate mu cap, you were using x bar, which is the sum of x over n. This is what we used earlier. Now, does it satisfy the first principle? Does that rule or formula satisfy the first principle, which means is it unbiased? What does it mean by is it unbiased? Is the rule or formula, that is the point estimator that I have in front of me here, the sum of x over n, our mu cap, which is the sum of x over n, is this unbiased? This is our first question. How do we know about that? What does it mean? First of all, let's try to understand intuitively what it means, and then we look at this mathematically. What does it mean by the fact that it should be unbiased? Unbiasedness means what? An estimator is said to be unbiased if the expected value of the estimator is equal to the true value of the parameter being estimated. All right. If we take, for example, the population for a certain industry, let's suppose, all right, where you have 10,000 individual in that industry. And then let's suppose we know what is the true average salary of these people in that industry. And the true average salary of these people in the industry is, let's suppose, 30,000 rupees. Now, this is the true salary. But as you will note, it's, as I'm saying here, let's suppose we know it. But generally, we don't know these information. So what we do, we want to estimate that mu, and we don't know whether it is 30. We have no idea about that. So what do we want to do then? We take a sample, and from that sample, we are going to compute the mean, as I said here. And that mean that I'm going to get will be a point estimate of this mu, and it will not necessarily be equal to 30,000. It could be 27,000. It could be 20,000. I don't know what it could be. But the question that we need to ask ourselves is that formula that I have used, which is sum of x over n, is it really appropriate to estimate that mu in a way that it is unbiased? Is it appropriate? So the first thing is that you need to know what it means by unbiased. It means that if you were to apply that formula, I repeat, if you were, you won't do it, but if you were to apply that formula for all the different possible samples that exist in the data, let's suppose you took a sample of 30 individuals. You have 10,000 and you decide to take several possible samples of 30 individuals. So in other words, if you are to take several samples of 30 individuals, you will have x bar 1, x bar 2, you will have different possible sample means, and millions, I don't know, it would be 10,000, C30, millions and millions of possibilities of having sample means. And if you were to take all the possibilities that exist of these different sample means that you got, and you do an average of these sample means, if you do an average of all these sample means, if that using that formula, obviously, all right, if you do an average of all these different values that you got through that formula, and let's suppose you get the true mean 30,000, then it means that this formula is unbiased. But if you use a certain formula, whatever formula, let's suppose I use n minus 1, and then I'm applying n minus the sum of x over n minus 1 to get the sample mean here, the different sample means. And if I take the average of all these different sample means that I've got using this formula, you might see that it is not going to give me the true mean 30,000. Then this formula divided by n minus 1 is a biased formula. So what do we want to do? We want, as far as possible, to have the principle of unbiasedness. All right. So in other words, if you were to take all these different possible sample mean, the millions and millions of sample mean that exist, if you were to sample mean means you have applied this formula for each of them, and if you were to use the average of all of these different possible values, you should get 30,000. And if you get 30,000, it means that it is unbiased. What is unbiased? The formula here, that is the point estimator mu cap is unbiased. All right. This is what we mean intuitively. But what about mathematically? Does this make sense? But mathematically, we say that intuitively, it kind of makes sense what I just explained here. All right. But let's try to understand mathematically whether this holds true. Whether the mean x bar, that is equal to the sum of x over n, is unbiased. How do we get to know that? We need to show that the average of our point estimator here is equal to the true value. All right. So expected value of mu cap, for example, in our case, we need to show that it is equal to mu according to this rule here. If you really want to know if it is unbiased, we need to show that the expected value of mu cap is equal to mu. Let's try to do that mathematically and see what we get. We say that the expected value of mu cap should be equal to mu. So let's try to know what is mu cap first of all. We all know what mu cap is. It is expected value of x bar. We decided to use x bar as a rule or formula. Obviously from an intuitive perspective, but also you will see that it is unbiased. Now, we know that the expected value of x bar is equal to the sum of x over n. So if it is equal to the sum of x over n, and we are taking the expected value of sum of x over n, we know that this is a constant. We can take the constant outside the expectation, and then we will have the expected value of a sum of x. Now, this is something that I already mentioned in the central limit theorem. When you're talking about expected value of a sum, you can also interchange their position. I already discussed that in the central limit theorem video, which means that now instead of having the expected value of a sum, you can have the sum of an expected value. All right, like this. Please refer to the central limit theorem to understand what I just did here. All right, the central limit theorem video, you will understand what I did. 1 over n, the sum of what is expected value of x. We also know from the past lecture when we did central limit theorem, we know that by definition, we decided to say that expected value of x is mu. We also learned last time that by definition, expected value of x bar is still equal to mu as well. All right. So what do we want to do then? If expected value of x is mu, we replace the expected value of x by mu. And this is equal to 1 upon n multiplied by what? You are summing a certain constant n times. Here, it's not written explicitly, but you understand that this is being summed n times. N times mean the sample size. All right. So if you are summing the constant n times, a constant is summed n times, it becomes n times the constant. So in other words, you will see that through this formula, you get an unbiased point estimator. All right. Through that formula, that is sum of x over n, you get an unbiased estimator in the end because you have been able to show that the expected value of mu cap equal to mu in the end. So the average of your averages equal to the true average. That is the principle that we've just seen in terms of unbiasedness. I explained it to you from an intuitive perspective, but I'm also explaining it to you from a mathematical perspective. Of course, we also have the sample proportion case. You have a case of sigma, all right, which in fact I would ask you to do here. I ask you to show that the x bar is equal to 1 upon n sum of x, then unbiased estimator of mu. This I already did for you, but I also asked you to do that. Show that s squared is equal to 1 upon n minus 1 sum of x minus x bar squared is an unbiased estimate of sigma squared. So we're going to do that in a moment, all right? But we'll take it last. But note something here. You see, you are not dividing by n, but dividing by n minus 1. Why is it so? We'll get back to that in a moment later on. So this is the concept of unbiasedness. Now, what about efficiency? What about efficiency? Efficiency relates to the concept of variance. Unbiasedness relates to the concept of average. You are talking about the expected value of a certain statistic or a certain point estimator. So you are talking about accuracy. When we talk about unbiasedness, we talk about accuracy. Okay, we refer to accuracy, which is referred to as the mean or an average. When we talk about efficiency, we talk about precision. In statistics, these are different terms. Precision and precision relates to variance. All right. So an efficient estimator is one which has got a smallest variance. So we'll get to understand what the efficiency means now. All right. The most efficient estimator among a group of unbiased estimators is the one with the smallest variance. This is what we refer to as the concept of efficiency. Let me just take a small example to illustrate what I'm saying. Let's suppose you have a certain random variable for which the mean of that random variable, or the mean of that point estimator rather, all right, for example, let's suppose I take expected value of mu cap. I'm just going to take this example to illustrate what I'm saying. The expected value of mu cap, we know that it should be equal to mu, all right. So if we are using a certain estimate, if we are taking a certain point estimator mu cap, and from mu cap you get mu using that point estimator, all right, then let's suppose this is mu cap. You are using, forget that for a moment. If you are using mu cap, a point estimator, which is our x bar, you know that we can have a distribution for x bar through the central limit theorem, which I already explained to you earlier. But if you take that point estimator mu cap and you get mu, it means that this estimator mu cap that you are using is an unbiased estimator of mu. This is what we learned already. So the mean of mu cap, the expected value of mu cap, is equal to mu. Now we can take this from a more general perspective rather than talking about mu. We can say that the expected value of theta cap is equal to theta, means that theta cap is an unbiased estimator of theta. This is what we can understand. Theta cap is an unbiased estimator of theta. So instead of talking about mu here, I'm going to refer to them as theta. Let's call this one theta cap 1. Let's give it a name. Theta cap means it's a rule of formula that you are using to estimate your theta. Theta can be anything. It can be, for example, mu. I'm just keeping it general. I'm not using mu. I'm just leaving it as something general. But bear in mind what it means. It means a formula or a rule that you are using to estimate your true parameter here. Same thing. So here it's like theta cap represent your mu cap and theta represent your mu. Another example, theta cap could represent sigma squared cap, and then theta represents sigma squared. There are other possibilities if you want to estimate the median, for example, or you want to estimate any other type of quantity. You are not forced to estimate only those different parameters that you are used to, the mean mu, the variance sigma squared, variance sigma, and p, but you might be interested in estimating some other quantities like the first quartile or whatever, I don't know, whatever measure you want to compute. If you are using a rule to estimate that measure, then that expected value of that rule of that formula that you are applying should be equal to 0. Now, what do I mean by the formula that you're applying? Maybe some of you might be a bit lost about that, but let me just remind you about the central limit theorem. For us, if we take the example of mu cap and mu, in fact, mu cap represents our x bar. This is what mu cap represents. Mu cap is equal to x bar, sum of x over n is a rule of formula. Now, we all know that we can have a distribution for x bar. This is something that we learned earlier. So if we can have a distribution for x bar, it means that you can have a distribution for, which means that basically you are talking about a distribution for mu cap, or you're talking about the distribution for theta cap, whatever it could be. So let's suppose for a moment that this represents this scale that you have here is for theta cap 1. And not only for theta cap 1, but also for theta cap 2. All right, you have two different estimators, means you have two different formulae rather, that you can use to estimate your theta. There are two different formulae that you can use to estimate your parameter. I'm leaving it as general here. I'm not talking about the mean. I'm not talking about the standard deviation or anything. I'm just leaving it as general. So you have theta cap 1 estimating theta and theta cap 2 estimating theta. Two different formulae that you are using to estimate theta. The next question that you need to ask yourself is, among these two formulae, let's suppose I've got two formulae that can be used to estimate a certain parameter theta. And both of them, as you are seeing here, they are unbiased because the mean of both are equal to theta. Theta cap 1, its mean, is equal to theta, and based on the diagram, you see that the expected value of theta cap 2 is equal to theta. So both of them are unbiased. But if you have two formulae estimating theta, and both of them are unbiased, and still you see that there is a kind of difference between these two. The question that you need to ask yourself is, which one shall you use? Which formula? Shall it be this formula, that is this formula, or shall it be this one? Shall we use theta cap 1 to estimate our theta? Shall we estimate theta cap 2 to estimate our theta? If both are unbiased, that's already the first principle that is being satisfied. But we need to go further and check which one will give us a more precise solution to estimate theta. Both of them are accurate, but which one gives us a more precise solution to estimate theta? And obviously, in this particular context, it is theta cap 1 that gives us the most accurate formula, not accurate, but the most precise formula to estimate theta, because it is the one with the smallest variance. Both are unbiased, but theta cap 1 is the one with the smallest variance, which means that theta cap 1 is the best suited rule or formula that you would be using to estimate theta. All right, so here, this is what I'm trying to show you, is that you would prefer to use, in this particular case, you would prefer to use theta cap 1 instead of theta cap 2 because theta cap 1 is the most efficient estimator in this example. Is the most efficient estimator. This is what we refer to as efficiency. So remember, if you were to use, which one would you use? Obviously, you would use the one with the smallest variance, and this is what we call theta cap 1 in this particular example. I repeat, these are different rules or formulae that you can use to estimate a certain quantity that is unknown. So we can take also the example of, we can take another example now, where you have, you can take, for example, the case of the variance, where you have two different formulae. For the variance, you have two different formulae that I will present, or I've already presented to you maybe. For example, there is one formula that you have 1 upon n minus 1 sum of x squared, which is used to estimate sigma squared. And there is another formula that you can use, which is also sum of x minus x bar to the squared, which you can use to estimate sigma squared. But which one shall you use in this particular context? We are not referring to the concept of efficiency. In this particular context, you will use this one because of unbiasedness. Not because of efficiency here, but we are referring to unbiasedness because this one is unbiased. This is why you will use this formula. I will get back to that later on anyway. But in our example here, this is why I'm showing you that in other cases, if you want to estimate whatever quantity, you don't have only one formula that you could use. You could have several formulae that are available, but there could be several formulae that are unbiased. All right, like here you have two different formulae, and one is biased, one is unbiased. In fact, this one is unbiased and this one is biased. So you prefer the unbiased one. But there are also cases where you can have several formulae which are unbiased, but one is better than the other, and it is the most efficient one which is better than the other. So that's a little bit about the concept of efficiency that I explained here. The most efficient estimator among a group of unbiased estimators is the one with the smallest variance. But there is something else I just want to note. I will take another example and ask you one question, all right, and see what is going to be your answer. You think about it. Let's take an example of another set of point estimators. You have two sets of point estimators, two different point estimators that can be used to estimate theta. But this time, you will see that there is a small difference between what we just showed earlier. This time, you will see that you have theta cap 2, which is here, and theta cap 1, which is here. And you will see that the expected value of theta cap 2 is equal to theta here. But you will note that expected value of theta cap 1 is not equal to theta. So my first question is, what does this mean? Think about it for a moment. You may pause the video and think about what this means, and then you can get back and play it again and see what the solution is. So just take a break for a moment and think about this question. If you have expected value of theta cap 2 is equal to theta, and expected value of theta cap 1 is not equal to theta, what does this mean? Just take a small pause and think about that for a moment. After having thought about it, now you need to understand that this means that this theta cap 2 is an unbiased, theta cap 2 is an unbiased estimator of theta. However, theta cap 1 is a biased estimator of theta. That is what it means. Now look at my second question to you and think about it before you continue the video. Take a break. Just after you get my question, take a break and try to think about what I'm going to ask you, and then you play the video again. My next question is, if you were to choose between theta cap 1 as an estimator to estimate theta, I repeat, when I talk about an estimator, it means a formula. I don't know what formula. It could be x cubed over 3 plus 1. It could be whatever it is, x cubed over 3 plus 1. It could be any kind of formula that can be used to estimate a certain quantity. All right? X cubed or anything. It could be, I don't know, whatever it could have been to estimate a certain quantity that is theta. Now, I repeat, which one would you prefer? Would you prefer to use, when you look at the diagram as it is here, and when you have seen what I've just showed you here, which one would you prefer to use? Shall you prefer to use theta cap 1 or theta cap 2 to estimate theta? Which one shall you use? So just take a small break, make a pause of a video right now and think about it for a moment. Think about it, and then you play the video, and then you will understand what I mean. So the question is, which of theta cap 1 or theta cap 2 shall you use to estimate theta? If you were in my place, which one would you use? Let me explain to you what I would have used. I would have used theta cap 1. I'm sure that many have answered theta cap 2. Many of you have answered theta cap 2 because you say that one of the desirable property of a point estimator is that it should be unbiased. Indeed, based on that fact, the logical choice would be to choose theta cap 2. But we also need to think a little bit more than that and be more logical in our approach here. We say that we want to have desirable properties. They are desirable properties, but at times we might have to sacrifice them. Like in this particular context here, it would not make sense to use theta cap 2 at all to estimate theta. It would make sense, on the other hand, to use theta cap 1 to estimate theta, even if theta cap 1 is biased and theta cap 2 is unbiased. Why? Because you have to think about this for a moment. When you are going to select one value from theta cap 2, normally, remember the x bar case, all right? And you are estimating mu out of it. You will have different possible values of x bars here on the scale. But in real context, in a real situation, you don't take several values. You don't take 1000 x bar, but you take only one of these x bar. It's from a random sample that you get this. And the value of x bar that you can get will be any value on that scale, can be any value on that scale, which could be quite close to the true mean mu, or it could also be far from the true mean mu. So, in other words, it's the same thing that I'm talking about here when we talk about a theta cap 1 and theta cap 2. You have a scale of theta cap 1 and theta cap 2 here on x. In real situation, you won't take all these different possible values of theta cap 1 and theta cap 2. You will take only one possible value of them. And that only one possible value from theta cap 2. Just imagine if theta is the true parameter, which is here, from theta cap 2, you have a high probability. Probability means, look at this area here. You have even a very high probability of choosing something that is very far from theta. You see? You have a high probability, look at the diagram. You have a high probability of choosing something far from theta. But if you look at the case of theta cap 1, you will note that the same probability. Let's suppose I take a value that is far from theta, a value that is far from the true mean using these two estimators. Let's say I choose a value here. This value from theta cap 2 is a possibility. There is a high probability of obtaining this kind of value very far from theta with theta cap 2. But from theta cap 1, this probability, just look at theta cap 1, the shape, it's almost close to zero. There is a very, very, very almost no probability of getting a value that far from theta. So remember that you're taking only one of these theta cap 1 or one of these theta cap 2. So if you have a high probability of getting something very far from theta cap 2, if from very far from theta, sorry, using theta cap 2, then it is of course a danger. It would be preferable to use another estimator that will give me a very higher probability of getting something close to theta cap 2, to theta, excuse me. So theta cap 1 is the one that is giving me a higher probability of getting something very close to theta compared to theta cap 2, which does not necessarily give me a high probability of getting something very close to theta, because you also have a possibility of getting something very far from theta. As you are seeing here, look at these probability. You still have probabilities here of getting something far, very far from theta. But this kind of situation will not happen with theta cap 1. So even here, if it is biased, because of the fact that the variance is very small, this is not talking about efficiency here. I'm not talking about efficiency. I'm not saying that theta cap 1 is more efficient than theta cap 2. That's not what I'm talking about here. Because bear in mind, the concept of efficiency relates to unbiased. Both of them should be unbiased. But here, in this particular context, because the variance is very small and very close to theta, this is why I would prefer to choose theta. But you have to be careful. If I get the same kind of situation where the variance is very small now and is very far from theta, obviously I'm not going to use this one. Let's suppose I've got another theta cap 3. Let's take another example. I've got another theta cap 3, which also gives you a very small variance like this, very small variance like this. All right. So, but it is very far from, this is theta cap 3. Theta cap 3. But it's very far from theta. Obviously, you won't use theta cap 3. So this is what I'm referring to here. You need to be a little bit logical. It's not because it is unbiased that this one is better. In fact, it is not the best solution here. You prefer to forego or to sacrifice this desirable property of unbiasedness to use the other estimator, which will yield a high probability of getting something close to the true value compared to the other one, where the probability of getting something close to the true value may not be that case, not be high rather. So that's not efficiency here. It's just something that is just food for thought, all right? So that you can think about a little bit more on these different ways of selecting estimators. Unbiasedness efficiency is here. When you are referring to a set of unbiased estimators, which one is better? The one which is with the smallest variance. Not efficiency is not here. I'm not talking about efficiency. I'm just talking about something else. So let's get back to our two desirable properties that I just mentioned. We have unbiasedness, we have efficiency, and there is a third one. And the third one is what we refer to as consistency. Consistency can be defined as what you are seeing here. All right, or you can read it there, it's the same thing. It says that the probability of having a small difference, see, when you see this term epsilon in statistics, this referred normally to a small number. In mathematics, this represents a small number. Right? Generally, when you see epsilon, it represents a small number. This is why it is very important that you know how to write different Greek letters in statistics. For example, if you write epsilon, this is okay, But if you write sigma, this is not okay. You see, you might be confusing sigma with an epsilon. This is why when you write sigma, be very, very clear in the way you write it. It should be very clear, something like this. And epsilon is something like that if you want. So always ensure that when you write down your Greek letters, you write it properly. For example, when you write the mean, mu, you see the way I'm writing it, don't write something like that. Some people do write this kind of thing in mu. This is not mu, this is a kind of m or whatever it is. Write it down properly, please. It's like a U with its long tail on the left, all right? So just write down your Greek letters properly. Now let's get back to this. The probability of having even a small difference between what you are estimating and your true value will tend towards zero as your sample size increases. That is, as your sample size tends to infinity or your sample size is large. This is what consistency is about. Let's try to understand that for a moment. Okay, what do I mean by this? Theta cap represent what you are estimating and theta represent what you have as a true value. Let's suppose I know the true value is 10. And let's suppose I'm estimating theta cap. And let's suppose I get theta cap to be a value of 5 for a sample size of 10. If I'm using a sample size of 10, I get theta cap is equal to 5. Now, again, if you are having difficulty to understand what theta cap is and what theta is, I'm just reminding you that theta cap can be any estimator of anything, of any quantity. This is why we are using a general term. I'm not using the mean to explain that because theta cap, the principle doesn't apply to the mean. It applies to any estimator that I'm talking about, even for the case of variance or anything else. But if you are having difficulty, just remember that when I talk about theta cap, just remember theta. Just remember mu cap, all right? And just remember mu. Theta is mu and mu is theta cap, all right? Is mu cap is theta cap and mu is theta. Just remember it like that. Where mu cap is your x bar that you are estimating mu the true value. So this is just to make things easier for you if you are having difficulty to understand what I'm talking about. But I'll stick to this theta cap and theta so that we are consistent with what is in the slides. Now, if you take the example of having theta cap and theta, you see there is a difference of 5. So if you take 5 minus 10, the modulus, you get 5, a difference of 5. So the probability of having a number 5 exists, but we don't know what it is. But let's take another example now. Let's suppose now for a higher sample size, you get 30, right? So here, when you look at the difference between 5 and 10, you get 5. So the probability of having a certain number is not necessarily 0 here, but it exists, all right? But let's suppose you decide to increase your sample size. What is supposed to happen according to this principle? According to the principle, what we understand is that if the sample size starts to increase, the difference, the probability of having the difference, which is greater than a certain number, all right, that is whatever number it could be, greater than 1 or greater than 2 or things like that, the probability of having a certain difference should get closer to 0, which means that if my sample size is 30, now if I'm estimating theta, I'm not expected to get, for example, 5, but I'm expected to start to get something like 7, where now if I take 7 minus 10, I get 2. Now the probability of getting even a smaller difference, is getting smaller and smaller. In other words, if I increase the sample size more now, n to 100, you might see that now my theta cap will become very close to 10, maybe 9.5. So the more I increase the sample size, this principle is showing me the more I increase the sample size, which means that the more the sample size gets larger and larger and larger, it means that the probability of having even a small difference, the probability of even having a small difference will get close to zero or will get very close to zero. It will tend towards zero. So the probability of getting a small difference will get close to zero. This is what consistency is about. What would happen? Let's suppose if I'm taking n is equal to 10, I get a difference of 5. And then if I take n is equal to 30, I get an estimator of 3. And if I get n is equal to 100, I get an estimator of 1. Then if this were the case, if for n is equal to 30, I get 3, n is equal to 100, I get 1, and n is equal to 10, I get 10, it means that it is contrary to the principle that you are seeing here, because it's not the case that when the sample size is increasing, your difference between these two numbers is getting smaller. No, the difference between these two numbers are not getting smaller, but they are increasing. They are going against this principle here. So if you have something like that, as sample size is increasing, the difference between what you are estimating and your true value start to increase rather than decrease, then it means that it is inconsistent. Your estimator is inconsistent. But your estimator is consistent only if you observe what I showed you earlier. Like when you are increasing the sample size, the difference between what you are estimating and what you have as true value should get smaller and smaller and smaller, and the probability of even having a small difference will get close to zero. That is the principle. All right. So the probability of having even a small difference will get close to zero if your sample size is very large or tends to infinity. So the bias will get smaller and smaller. The bias means the difference between these two here, the difference between what you are estimating and your true value. So that is the concept of consistency. The value of the estimator gets closer to the parameter as sample size increases. Consistent estimators may be biased, but the bias must become smaller as the sample size increases if the consistency property holds true. This is what I'm showing by the bias here. In other words, an estimator is consistent if you have this property holding true, as I showed you. So a quick reminder is that the probability of having a differences here being greater than a small number, in other words, the probability of having even a small difference will be very close to zero if the sample size tends to infinity. Right? Will be very close to zero means it is almost inexistent. If the sample size is very, very large, the probability of even a small difference is having even a small difference is inexistent. It's going to be very, very, very low. That is what consistency is about here. So, in a nutshell, what is a point estimator? Point estimator is a single value that you are using to estimate a certain number. Remember that you don't have several values, you have only one value of theta cap, all right? Whatever theta cap could represent, but you get only one value to estimate a theta, whatever parameter. So I already discussed that earlier. I showed to you that the expected value of x bar is equal to mu. I've already shown this to you. Now I want to do something else. I want to show you that normally, if you want to estimate variance, if you want to estimate mean, you all know how to calculate mean. It is the sum of x over n. But now, if you want to estimate variance, logically, many of you would think about this formula because this is the formula that you have learned so far. The logical way of thinking about it is that, okay, if I want to estimate the true variance, I need to apply this formula on the sample to get an estimate of my true variance sigma squared. But you will see that if you were to do this, there would be a small problem. The problem that you have with this estimator, with that rule or that formula to estimate sigma squared, that is this point estimator, is that the problem with it is that it is a biased estimator. It is a biased estimator. Therefore, what happens is that instead of using this formula 1 upon n, normally what we do is that we use another version of that formula. We use a version where you divide by n minus 1. Why do you use this version of division by n minus 1? Because this version becomes an unbiased estimator of sigma squared. And given that unbiasedness is one of our desirable properties, we might want to abide by that. And if we want to get that, then instead of using the divide by n formulae, which is a biased one, it would be preferable to use this divide by n minus 1, which is an unbiased one. Unbiased with regards to what I already explained to you what it means by unbiased. So henceforth, what you need to understand is that we are going to use this formula to work out, to estimate your population variance. All right, to estimate the population variance, that is what we are going to use now, henceforth. Before we get into the proof, the mathematical proof of this formula, maybe I would prefer just to explain to you how to apply the sample, the sample mean and everything. All right, how to apply this principle of point estimate. Let's suppose I take three very simple example of 2, 4, and 6 as a set of numbers. And then this represent your sample from a certain population, all right? And you are asked to estimate, for example, the true mean mu using a point estimator. If you are asked to estimate the true mean mu using a point estimator, the logical point estimator that you know that you should use is x bar, and this is equal to 1 upon n sum of x, which basically means 1 upon 3 times 2 plus 4 plus 6. That's what you have. So in other words, it is 12 out of 3, and this is equal to 4. As simple as that, you get a single value that is used to estimate a certain unknown quantity mu that you do not know exactly. It's an estimator of mu. Now, that is one thing. But let's talk about the other thing. We want now to estimate the variance. This is our next step, to estimate the variance. Now, to estimate the variance, as I said to you, there are two possible ways of estimating the variance. 1 upon n sum of x minus x bar to the squared, which in fact we use the other formula sum of x squared over n minus x bar to the squared. We used that last time. All right, which means what? Let's apply this one first, and you will see that this is different from the one that I'm going to explain in a moment. That is divided by n minus 1. You will see that it is different. Obviously, it's going to be different because they are surely different, but let's show how different they are in this particular context. So here it means what? If I were to apply that, it means 2 to the squared plus 4 to the squared plus 6 to the squared over 3 minus the mean that you've got, 4 to the squared, and this would be 2 to the squared plus 4 to the squared plus 6 to the squared, which is 56 over 3 minus 4. And normally, if you do the computation, you will see that you are supposed to get 2 point, just a minute with you. You are supposed to get 2.67, all right? This is using this formula. But what about if I use the other formula now? Look at what the variance you get here. Eh? The variance is 2.67 normally. Now, if you use the other formula, which is the formula that I gave here, which is defined as s squared, just like you have x bar to estimate mu, you have s squared that can be used. So in other words, you can estimate sigma squared using s squared, which is equal to 1 upon n minus 1 sum of x minus x bar to the squared. Now, but before we move on this one, let me just change the slide and show you something. You have s squared is equal to 1 upon n minus 1 sum of x minus x bar to the squared. You may use this formula on your data 2, 4, and 6 that we just used. You may use the formula directly, but you can also use an alternative version of this formula. All right. The alternative version of this formula is, instead of using 1 upon n minus 1 sum of x minus x bar to the squared, you may wish to use this one, right? Sum of x squared minus n x bar squared over n minus 1. Or you can use this one as well. That is sum of x squared minus sum of x to the squared over n, and the whole thing you divide by n minus 1. These are going to give the same solution. Whether you use this, or you use this, they're going to give the same solution. All right, they are not different. All right, they are the same thing, but just expressed differently. All right, just remember that. You can use this formula if you want. Any of them will give you the same solution if you were to apply them. So maybe I'll use this one. All right, so I'll use this one. So this one means what? S squared is equal to the sum of x squared, which is 2 to the squared plus 4 to the squared plus 6 to the squared. And then what it says, I need to subtract n, which is 3 times the x bar, which we saw was 4 to the squared earlier. And then you need to divide by n minus 1, which is 2. All right, so you are basically dealing with 56 minus 3 times 4 to the squared divided by 2, which is equal to 48 divided by 2, and it's equal to 4. 8 divided by 2, which is equal to 4. This is our variance from this formula. So if you are asked to estimate the true variance, you are expected to use this formula because it is the unbiased one. The previous one, you saw that it gave you a value of 2.67 close to 3, but this one is giving you a value of 4. They are quite different, all right, especially because you're dealing with small data here, but it's important that you make use of this one. Remember, you could use this one as well. It's the same kind of approach. The only difference with this one is you will do it like this. If you were to use this one, you will say 2 to the squared plus 4 to the squared plus 6 to the squared. Subtract 2 plus 4 plus 6 to the squared, divide by 3. The whole thing you divide by 2. All right. And you will see that again, this will give you 4. So that is how you were to apply a point estimate. It's very simple. It's just an application of a formula and you get your solution. And as you are seeing in any of these formulae that I'm applying, you are getting only one value to which is a point estimate. All right. So a single value. Now, just back to what we wanted to do. We wanted to show that this one is an unbiased estimator of sigma squared. That is, this formula is an unbiased estimator of sigma squared. Now, if you want to show that something is an unbiased estimator of sigma squared, it means that you need to show that the expected value of s squared equal to sigma squared. That's the only way to show that it is unbiased, because this is what I explained by unbiasedness. I explained to you that the expected value of theta cap equal to theta if they are unbiased. So what is theta cap here? Our case theta cap is our s squared, which is sigma squared cap. All right, which is sigma squared cap. So therefore, if the expected value of sigma squared cap, which is s squared, is equal to theta, which means sigma squared, then s squared is an unbiased estimator of sigma squared. But if it is not the case, if it is not equal to sigma squared, it is a biased one. So let's try to work this out. It's always good for you to understand a little bit why we are doing these things, all right? Now, this part is not necessarily, this mathematical part is not necessarily examinable for you students of statistics for finance. All right. For students doing statistics for finance, this part is not necessarily examinable, but this is something that is examinable for other students who are doing other statistics module. But for students who are doing statistics for finance, that is for you students doing statistics for finance, this is not necessarily examinable, but this is examinable for other batches of students who are doing statistics as their main subject or actual studies. These kinds of things are examinable, but for you, no. But still, I'm just going to show you how it is so that you understand what I'm talking about by unbiasedness. All right. So we say that the expected value of s squared should be equal to sigma s squared. So let me just illustrate that for you mathematically. Is it true that if I use divide by n minus 1, is it true if I use this formula, I get sigma squared in the end? So we're going to try this out. I'm just going to show you that there are certain principles in mathematics that you may not totally get, but I will try my best to explain that in a matter of seconds. But if you don't get it, you do not need to worry too much, but just follow exactly what I'm doing. If we do the expected value of s squared is equal to sigma squared, we want to prove that, we need to show what s squared is. Here is s squared. S squared is 1 upon n minus 1 sum of x minus x bar to the squared. Now, you all know what expectation is. Expectation is like a summation in itself. If it is like a summation, it's the same property like a summation, so you can take a constant outside of the expectation. So you have 1 upon n, expected value of the sum to the squared. All right, this is what you get here. Now, what we might want to do is to expand this first before we move on. Let's try to expand this a little bit, expand this first before we do anything else. So we have the sum of here we go. We have expected value of, we bring the summation inside here. So we get the sum of x squared minus 2x bar sum of x plus sum of x bar squared. This is what we get. Sum of x squared stays as it is, but if you look at the sum of x, for those who don't know, x bar equal to the sum of x over n. So if we want the sum of x, to simplify the sum of x, we can just say that it is equal to n x bar, excuse me. Can just say that it is equal to nx bar. So in the end, you will see that this turned out to be nx bar squared, because you have nx bar times 2x bar, it becomes nx bar 2nx bar squared, plus x bar. If you're summing a certain constant x bar, you have only one possible x bar that you get when you're doing something. So in other words, it is a constant, and if you are summing it n times, it becomes n times the constant x bar squared. So finally, you are left with minus nx bar squared. Why? Because minus 2nx bar plus nx bar becomes minus nx bar squared. So let's continue from there now. You see, if you just take it as it is here, you won't be able to do much, except if you do something else now. If you start by interchanging the summation with the expectation, you can do that. I'm just going to briefly explain this to you in a moment. But first of all, I interchange the sum with the expectation. So I bring in the expectation in there. First of all, you have the expectation of the sum of x bar squared, which in the end becomes the sum of the expected value of x squared minus the expected value of n x bar squared, which becomes n, a constant, and then expected value of x bar squared. Now you have to be careful here. You will see that in this particular context here, I've considered it as a constant, but here I'm not considering it as a constant where I can say that it is equal to nx bar squared. No, I can't do that. Why? Because expected value of x bar means that you are dealing with a random variable now. Now it is considered as a random variable. The moment that you use the term expectation in something, expectation of x means you are dealing with a random variable. The moment that you put the expected of anything like x bar, you are dealing with a random variable in this case. All right, except if it is a constant, that's a different thing. If you're dealing with a number a, expected value of 2, it's a different thing. But now, because you are talking about expected value of x bar, I cannot say that I'm going to remove x bar outside and consider it as a constant. It is considered as a random variable now. All right, the expected value of a random variable is being considered now. So let's continue on the next slide. All right, I'll just rewrite this down here so that we don't get lost. So this is the equation that we wrote, all right, and it's nx bar squared, and expected value of x bar squared, and the sum of expected value of x. So now when we reach that point, we need to think about a little bit what we are going to do from here. What shall we do from here? Let's try to figure out. Expected value of x squared is what? To be able to know what expected value of x squared is, we need to know certain principle. We need to know that the variance of x is equal to the expected value of x squared minus expected value of x to the squared. So if this is what we already know, that the variance of x is equal to the expected value of x squared minus expected value of x squared, this implies that the expected value of x squared equal to the variance of x plus the expected value of x to the squared. See that? Expected value of x squared is equal to the variance of x plus expected value of x to the squared. Now, what is the variance of x? By convention, we know that the variance of x is sigma squared. This is what we learned in the central limit theorem. And we know that the expected value of x is mu according to the central limit theorem when we explain things there. So you have mu, but then you have squared. So you have sigma squared plus mu squared. So in other words, you know that this expected value of x squared can be rewritten as sigma squared plus mu squared minus n, and then you have expected value of x bar to the squared. Let's try to figure out. If expected value of x squared equal to variance of x plus expected value of x to the squared, it means that expected value of any other random variable, it could be z, for example, expected value of z squared equal to the variance of z plus expected value of z to the squared. Or it means that, I'm just going to write it down there, it means that the variance, that the expected value of x bar squared equal to the variance of x bar plus expected value of x bar to the squared. That's what it means. Let me just write it a little bit above here. So expected value of x bar squared is equal to the variance of x bar plus expected value of x bar to the squared. That's what it means, because we are just replacing it by x bar instead of x, that's all. And what is the variance of x bar? We have learnt in the previous lecture on central limit theorem that the variance of x bar is sigma squared over n. This is what we learnt earlier. Plus the expected value of x bar squared. We also know that the expected value of x bar is equal to mu from what we learnt, but of course there is a squared here, so it is mu squared. So we have understood that we can replace the expected value of x bar squared by sigma squared over n plus mu squared, which means that it is equal to 1 upon n minus 1. And then if you are summing sigma, let's suppose you sum sigma squared n times, you get n sigma squared. But if you sum sigma squared plus mu squared n times, you get n squared, n times sigma squared plus mu squared. Whatever the value that you got here, if it is a constant, because bear in mind that now sigma squared and mu squared are not random variable, but they are constant. So if you are summing a constant like n times, it means that it becomes n times a constant. So in other words, you have n sigma squared plus mu squared minus, you have, I can just bring this and cancel the n here. So you have sigma squared plus n mu squared here. Here we go. So we can just simplify this further. It becomes n sigma squared plus n mu squared minus sigma squared minus n mu squared. And what do you get from that? You will see that these two cancels out, leaving you with n sigma squared minus sigma squared, which means what? Sigma squared is common. So you have 1 upon n minus 1 into n minus 1 times n minus 1 times sigma squared. So what is up? N minus 1 times sigma squared is common. So n minus 1 cancels out, which gives you sigma squared. And this is what we wanted to prove originally, that we wanted to prove that the expected value of s squared is equal to sigma squared. What s squared? S squared where you divide by n minus 1. Now you may try to do the same thing, but without dividing by n minus 1, but rather dividing by n. And if you were to do that, you will see that you will not come up with sigma squared, but you will come up with the factor of sigma squared. It will not be equal to sigma squared, but a factor of sigma squared, which means that if you were to use the divide by n, you will not have obtained an unbiased estimator, but it would have been biased. So the only way to use to get an unbiased estimator is by using this divide by n minus 1. Now you now you understand why we are dividing by n minus 1. For those who did not really understand the idea of dividing by n minus 1, it should be clearer now that by doing this you get an unbiased estimator, as we have been able to prove it. So that's all for point estimator. So the next video will be on confidence interval.